And I told you distance, I think the example I gave was like if I'm standing here and I walk. You know, displacement is how far am I from where I started. So if I start back there and I walk all the way back to where I started, my displacement is 0 because I am where I started. But if I measure the distance I walk, you would have to add those two together. So distance is like the absolute value. Displacement would just be your regular integral. Helps if you turn that on.
Do you have a scar in your ear? Do you have makeup
I might have a scar actually.
Yeah, right there. I just didn't.
Oh, yeah.
I've never seen it before, but I wanted to make sure you didn't just have like a smear of makeup. It's not at all.
Okay, so if we look at this one, we have a particle moves along a line so that its velocity at time t is given by this equation. Okay, it's measured in meters per second. T is our time. So find the displacement of the particle during the time period 1 to 4. What does displacement mean?
How far you are from the start.
How far we are from the start. So displacement just means do the integral. So for part A, I'm going to integrate from 1 to 4 of my equation. Okay, so the antiderivative of t squared minus antiderivative of t 1/2 minus antiderivative of 6 Alright, so if I plug in my forward, and I think.
Negative 4.5. Yeah. This calculator is really picky. If you have an extra parenthesis in here.
Oh yes, it does not like that.
I just want to make sure I have all my parentheses closed, but obviously.
And why? What does it mean when your displacement turns out to be negative?
You are the opposite. You were like under the line from where you were.
Under the axis. Okay.
No glasses.
Oh, okay. You
can ask her. She has the schedule.
No, well, it's not right now. Part B. Find the distance traveled. How do I do distance traveled?
Add them all up.
Okay. So what we have to do is do the absolute value so that we can do each little time period and add them together. So for the absolute values, we need to know when this is going to equal 0. So if we factor it, t minus 3t plus 2 equals 0. We get 3 and negative 2. But we only need the time period that's in my integral. Plus time can't be negative anyway. So we're going to integrate from where to where?
1 to 3.
And then
3 to 4.
between 1 and 3, easiest option, just plug in the number. If I put in a 2, is this thing positive or negative? So 2 squared is 4, minus 2 is 2, minus 6, negative. So the absolute value would do the opposite. So I'm going to change all those signs. Between 3 and 4, if I put in a 4, for instance, 16 minus 4 minus 6, that is, so it does not change. All right, try to finish it.
I did it right.
That's fraction forms, we're not counting. I don't know if that's right. Did I skip them? No, that was. Okay. Let's get our books for a minute, and I want to turn to page 403 and look at a problem. I was just lazy and didn't retype it. Sorry.
My book is on my bed, so I'm gonna just
Just share.
I'm gonna just get my big magnifying glass out of them.
All right. So page 403, example 7. So just cover up the answer. Don't look at that right now. We really want to look at the graph. So figure 4 shows power consumption in the city of San Francisco for a day in September. P, the Y value is megawatts. T, the x-axis is hours starting at midnight. Estimate the energy used all day, or on that day. So this is giving us the curve. When I'm asking for the amount of energy used, I am looking for what? The area under the curve, okay? Now, do we have a nice formula for this? No. So essentially what we're trying to do is integrate it. We want one day, so from 0 to 24 for the 24 hours of this power function. But because we don't have the actual equation, we can't work it out, I just want to show you we can use the graphs to estimate those. Okay? What if we did, so we could do every hour, but that's a lot of work. Do you want to do like midpoint rule? Okay. Do you want to do change in x equals, the smaller the change in x is, we know the more accurate it will be. But we also want to be time efficient. So what do you want to do? Every 2, change in x equals 2 or 3? 3? Okay. So our answer will be slightly different if you're trying to compare the book because we aren't necessarily doing the same thing. That means we're going to add up. How many things will we be adding if we go every 3 hours? 8. And what would I have to multiply all this by? 3, because my rectangles are 3 wide. So the midpoint rule says if you go between 0 and 3, we are going to try to estimate based off the middle of that interval. So at like 1.5, what do you think your y value would be? 430? I already wrote 430. I'll roll with it. We're estimating. So between 3 and 6, 4.5 would be the middle. What does it look like it might be then? 405, 410, something like that. We know this is an estimate between 6 and 9, so 7.5. What does that appear to be?
660, 680.
Yeah, 680. Okay. Between 9 and 12. Okay, between 12 and 15. Just barely higher than the previous one. Between 15 and 18. Yeah, somewhere thereabouts. Between 18 and 21. 605?
705.
And between 21 and 24.
590.
So let's estimate it.
Wow.
If you look at the book, they did 2-hour intervals and they had, what, 15?
15, 4 hours.
Yeah, so we were pretty close in our approximation. So really thing there, just understanding that if we're looking for the amount, that's the antiderivative on a graph, that's talking about area under the curve. All right, any questions there? Okay, so that is the end of the section. I did go ahead and give you that assignment Friday. I wanted to give you some time to work on that. I also would like to introduce the next section. So what do you want, work time first or introduce the next section first? Okay. The only reason I really want to get ahead on the next. So what I want to do is just a little bit off substitution rule. And we'll be practicing tomorrow. There'll be book problems assigned for those of you that are gone for the art show. So make sure you are checking that. So this is something we can use to do the antiderivative of things that we could not do the antiderivative of before. And so we're going to start out, I'm actually just going to skip the rule itself because it looks confusing. And I want to go straight to a problem. Now we have actually worked through problems like this before. So we're going to start with some more basic ones that we would have been able to figure out without the substitution rule. And then we'll get into the ones that we wouldn't have been able to do. So when I'm looking at these, we did some substitution like way back, solving quadratic type equations and things like that. You've seen like some different factoring, we did substitution. And it's basically a way of taking a more complex thing and looking at something simpler. So when I look at this, the 2x plus 5 is all to the 5th power. So that's kind of the ugly part, the inside of the function. So that's typically what we are going to substitute. So I usually just go with a u. So u is going to be the inside. Now du is the derivative of u. What is the derivative of 2x plus 1? 2, and I'm doing implicit, so I'm going to put a dx with it. Okay, another way of writing it, du dx is how we typically write that. And then you multiply over the dx. So when I look at this, the 2x plus 1 gets replaced with a u. So we have the antiderivative of u to the 5th. 2 dx is du. So u to the 5th du. Now, do we need substitution to do this problem? Absolutely not. You guys could have figured it out. But, are you with me so far?
Yeah.
This is an easier function to do the antiderivative of, isn't it? Antiderivative of u to the 5th, add 1 to the power, throw a 1/6 in front. We don't have anything to plug in, so it would get a plus c. Then the final thing is, at the end, I don't want u. What is u?
2x.
So the antiderivative is 1/6 times 2x plus 1 to the 6th plus c.
Is this going to make sense when we do harder problems?
Yes.
Okay.
Like on this one, it's totally unnecessary. So it's just extra work. But I want you to see how it works here. So we're basically replacing everything that has an x in it. So I had to replace this whole thing and my dx part. And it gave us a simpler function to look at. So if I look at this one, we could not have done that before because it has 2 x's being multiplied. Can we do a product rule in reverse? No. So this is where substitution is really required. When I'm looking at that, I'm trying to pick the thing to be my u. So u is like the inside of your function, or if you have multiple exponents, you're looking at the piece that has the higher power in it. So that would be what?
The square root.
Okay, the thing, and we don't want the square root itself, just the thing under it.
Right.
So I'm going to say my u is 1 plus x squared. So du. I am not looking back at the original problem. I'm just doing the derivative of this. And we usually just put the dx over on the right-hand side. So the derivative of 1 plus x squared,
2x dx.
2x you guys with me to that point? So now, we have to make those substitutions in our power. So we have an integral. The 2x and the dx together make up
2 dx. That's what I mean.
the 2x dx gets replaced with du. And then all I have is the square root of 1 plus x squared is, or we can think of it as u to the 1/2 du. That is a very easy antiderivative for us to do. Add 1 to the power, so that would be
2/3 plus 3.
And then what do we change u to?
1 plus x squared.
Because our original problem had x's, our answer has to as well. And just like any other antiderivative, you could do the derivative of this to check your answer. If I did that, my 3/2 comes down, cancels, 1 plus x squared is 1/2. Derivative of the inside is 2x. So we would get our original back. And do one more and then I'll stop. That way those of you that are gone tomorrow have at least seen a few of them, and then you can get the rest of the examples from the video. So we couldn't do the antiderivative any other way. What would u be on this problem?
And u would be x cubed plus 9.
Everybody agrees with that? So what is my du, the derivative of x cubed plus 9?
3x squared.
But then it, yes, but then it
So
doesn't
then
match
we do
up.
1/3.
So if I look, the x cubed plus 9, I need, that's going to be my u. I have an x squared and a dx, which is this part, but I don't need my 3. So what we can do is divide that over and make it 1/3 du is equal to the x squared dx.
Now it's feeling complicated.
So x squared and dx together get replaced with 1/3 du. You can put it at the end, you can put the 1/3 in the front and the du at the end.
Plus you.
Doesn't matter. And then we have the square root of u. Or think of that as 1/3 u to the 1/2 u. So antiderivative, add 1 to the power, multiply by the reciprocal, which is 2/3 times my 1/3, so 2/9. Everyone know how I got there? Am I done?
No, there's 3 plus 7.
So final answer, I don't want u. But u was x cubed plus.
Why did you divide by 3?
Because in my problem, I didn't need that 3 anywhere. Now, if I'd had like a 3x squared, I would have left the 3. But I didn't, so I moved it over so I could bring it in with my du.
If you're missing